Okay, now having seen the binomial theorem and its proof, we are now ready to see some of its consequences. So this is the expansion. Now in this expansion, a and b can be any real numbers and n is a positive integer. So what happens if we take special values of a and b? For example, replacing b by minus b, we get, in place of b, if we have minus b, then what shall we have? I varies from 0 to n, nc I a to the power n minus I minus b to the power I, and this can be written as minus 1 to the power I nc I a to the power n minus I b to the power I. Okay, so this is the expansion for a minus b whole to the power n. Now, if a is equal to 1, then what happens to this? If a is 1, then the left hand side becomes 1 plus b whole to the power n is equal to this factor, this power of a to the power n minus I, this will become 1. Summation I varying from 0 to n, nc I b to the power I. Okay, and if I put a equal to 1 here, then I get 1 minus b whole to the power n is equal to summation I varying from 0 to n minus 1 to the power I nc I b to the power I. Okay, so these two expansions are somewhat special and they appear quite often in mathematics as well as in application of mathematics to some areas of physics where we need this expansion, although in those places this n is not necessarily an integer. So that is something which is beyond what we have done. We will get to that, but it will take some time. Okay, we have to know the concept of an infinite series. There are some sums where instead of having a finite number of numbers, finite number of terms, we have infinitely many terms. So that part, we will get to that part. For that we need to start calculus, which is coming. Okay. Now we can further particularize this situation if additionally we have b also equal to 1, then taking a equal to 1 got us these two things. Now taking b equal to 1 in these two, we get, in the first one what will happen, if I take b equal to 1, on the left hand side I will have 2 to the power n. So 2 to the power n equals, this power involving b will vanish and I will be left with simply this sum that has the binomial coefficients. And we see that here we get a nice identity, nc0 plus nc1 plus nc2 etc. all the way up to ncn. So if we add all these binomial coefficients, then we get 2 to the power n, that becomes the sum. Whereas in the next one, if we put b equal to 0, the left hand side becomes 0 and the right hand side becomes this alternating sum, minus 1 to the power I nc I equal to 0 to n. So when I is 0, the minus sign will become plus, minus 1 to the power 0 is plus 1. So NC 0. When I is 1, it will become minus. So minus NC 1 plus NC 2 minus, it will go like this, plus minus 1 to the power n NC n. For the last term, we cannot determine whether it is plus or minus if we are not given what n is, or rather what is n's parity, whether it is even or odd. If it's even, then this will be plus, otherwise it will be minus ncn. Okay, so these two identities we get. Now let us look at some problems involving these expansions. So let us just first of all try to expand this expression where x is a non-zero real number. Since x appears in the denominator, it's necessary to add this condition, otherwise this will become meaningless. So we straight away apply the binomial theorem. 4c0 x square whole to the power 4 plus 4c1 x square cube times 3 by x plus 4c2 x square whole square times 3 by x square plus 4c3 x square times 3 by x cube plus 4c4 3 by x to the power 4. Now these binomial coefficients, their values can of course be found out using the formula for NCR, but more easily it can be found out using the Pascal's triangle. You see, it's not very difficult. We start with 1, 1, then we just generate the next rows. You already know the pattern. Each number except the extreme ones in the Pascal's triangle comes from the previous row by adding the nearest two numbers. So 2 comes from 1 and 1. So like that 1, 3, 3, 1, 2 plus 1 is 3. Then the next one will be 1, 4, 6, 4, 1. 3 plus 3 is 6, 3 plus 1 is 4. So these are the coefficients. This is 4c0, 4c1, 4c2, 4c3, 4c4. Okay, so we can, from here itself we know these numbers. So this is 1 and we have x to the power 8 plus 4c4 is 4 times x to the power 6 times 3 divided by x plus 4c2 is 6 times x to the power 4 times 9 divided by x square plus 4c3 is again 4 times x square times 3 by x whole cube. So this becomes 27 divided by x cube. Finally 4c4 is 1. 3 to the power 4 is 81 divided by x to the power 4. And this equals, if we simplify, plus 4 times 3 is 12. X to the power 6 divided by x is x to the power 5. 6 times 9, 54. X square plus 108. X square divided by x cube is 1 by x plus 81 divided by x to the power 4. So this is the expansion. So in this way we can expand using the binomial theorem. Now, using the theorem, we can also try to calculate some powers without actually multiplying the numbers. So what I am trying to say is that suppose you are given something like this, 98 to the power 5. If you want, you can of course multiply 98 with itself 5 times, or you can use the binomial theorem by writing 98 as 100 minus 2 to the power 5. Now before proceeding, okay, let us just first write the expansion and then we see what is the advantage of proceeding this way. So this is 10 square minus 2 to the power 5. So first of all, we just write the expansion, then take care of the values after that. 10 square to the power 5 plus 5c1 10 square to the power 4, and don't forget this is minus 2. So minus 2 plus, if you forget the sign, the game is over. 5c2 10 square whole cube times minus 2 square plus 5c3 10 square whole square times minus 2 cube plus 5c4 10 square times minus 2 to the power 4 plus 5c5 minus 2 to the power 5. Okay, now comes the question of the coefficients. So again we can use Pascal's triangle. The previous coefficients help us here because the previous coefficients were 1, 4, 6, 4, 1. So the next ones will be 1, 5, 10, 10, 5, 1. Just imply the you add the nearest neighbors in the previous row. So this is 1, 5, 10, 10, 5, 1. So the first term becomes 10 to the power 10 plus this is 5. Okay. Now 5 times minus 2 is minus 10 times 10 to the power 8. Minus 2 square is 4 and 5c2 is 10. So plus 10 times 10 to the power 6 times 4. 5c3 is also 10. But we have a minus sign and an odd exponent, so minus 10 times 10 to the power 4 times 2 cube is 8. Then after this we have 5c4. This one will be plus because the signs are alternating. You see 5c4 is 5. And from 2 to the power 4, if we take 1, 2 out and multiply that with this 5, that becomes 10. So that 10 times 10 square. So we took 1, 2 out, so we are left with 3 2's. That means 2 cube. So this is times 8. Finally, 5c5 is 1 and minus 2 to the power 5 is minus 32. So the sum looks like this. 10 to the power 10 minus 10 to the power 9 plus 4 times 10 to the power 7 minus 8 times 10 to the power 5 plus 8 times 10 cube. I have run out of space. Let me write it here. Minus 32. Okay. Look, you verify this calculation carefully, okay. It may happen that I have made a mistake in writing these exponents. Let me just see once more. 10 to the power 10, right? So here 10 to the power 8 and another 10. Here we have 5c2 is already 10, so 10 times 10 to the power 6 times 4, okay. 5c3 is 10, 10 times 10 to the power 4 times 8. 5c4 is 5, taking that with 1 2 gives me 10 times 10 square, and 3 2's give me 8 minus 32. So 10 to the power 10 minus 10 to the power 9 plus 4 times 10 to the power 7 minus 8 times 10 to the power 5 plus 8 times 10 cube minus 32. Yes. Now the thing is, why do we need this calculation? Why can't we just multiply these numbers and find the answer? We can if we want, but here you see the job has been made easier. Why? Because powers of 10 are very easy to find. 10 to the power 10 is nothing but 1 followed by 10 zeros. Okay, 1 2 3 4 5 6 7 8 9 10. So just like that, we can just write every term, and then all we have to do is add and subtract. So because 98 can be written as a difference of two numbers whose powers are easier to calculate than calculating this product. That's why we carried out this calculation like this. You can see now the job is much more easy than this finding this product out. It may seem like you can multiply these two and then take its square, but it will take some time. Still, the fact that here 98 is a somewhat convenient number has enabled us to approach the problem like this. In general, that may not be the case, of course. Okay. Let us take a different type of problem. So I write it as a question. Use the binomial theorem to show that six to the power n minus 5n leaves the remainder 1 when divided by 25 for all positive integers n. So what this question asks us is to show that when we divide the number 6 to the power n minus 5n by 25, the remainder is always 1. Now we have already obtained problems like this, although there we had to show that some number divides an expression like this, that is the remainder is 0. This is more general. This asks us to show that the remainder is 1. But so there what we did, we use mathematical induction, but here we have to use the binomial theorem. So how can we do that? one clue is that because we have a power, so somehow here binomial theorem will be used to expand this. Okay, and it is explicitly told that we have to use the binomial theorem. So the solution goes like this: 6 to the power n minus 5. So unlike mathematical induction, now our n is general. It's not that we have to first verify it for n equal to 1 and then proceed. It's not like that. Now n is any positive integer. So what we do, we write 6 as 1 plus 5 whole to the power n minus 5n. And this one we expand. So its expansion is easy. See, here it is of the form 1 plus b whole to the power n. So the expansion looks like this: nc0 plus nc1 times 5 plus nc2 times 5 square. Let me write one more term. We will realize why. nc3 5 cube plus etc. plus nc n 5 to the power n minus 5n. Okay, so till this we have the expansion and minus 5n. Now to make matters even more simple, we can handle some special cases. What special cases? You see, when n is equal to 1, although I said we don't have to consider n equal to 1, but to use this expansion effectively, we try to do away with some initial cases. Okay, so when n is 1, 6 to the power n minus 5n is what? 6 minus 5 is equal to 1. So when you divide 1 by 25, the remainder is 1. Why? Because 1 can be written like this: 1 is equal to 0 times 25 plus 1. Okay, where this 1 is greater than or equal to 0 and less than 25. So this is the remainder when you divide 1 by 25. And that turns out to be this number. So the result is true in this case. Although it sounds like induction, but this is not induction, because we are going to consider another case also. N equal to 2. If n is equal to 2, then 6 to the power n minus 5n becomes what? 6 square. 6 square is 36 minus 5 times 2, that is 10. So this is equal to 26. So this also leaves the remainder 1 when we divide it by 25. Why? Because it is equal to 1 times 25 plus 1. Right? So the result is true for n equal to 1, n equal to 2. Okay? So we can consider n to be greater than or equal to 3 because the other two cases have already been verified. Now you look at this sum. Along with this extra condition, n is greater than or equal to 3. Now in this sum, what is happening? You see, nc0 is 1 plus nc1 is n, that means this is 5n plus, starting from this term all the way up to this term, every term has at least 25. You see 5 square, 5 cube, from all of them we can take 25 common out. So if we do that, we will have 25 times NC2 plus NC3 times 5 plus etc. plus NCN times 5 to the power n minus 2 minus 5n. That extra 5n is always there. So these minus 5n and plus 5n, they cancel out. And we have something like this. NC2 plus 5NC3 plus etc. plus 5 to the power n minus 2 NCN times 25. These two terms are not there, plus 1. Now you look at this form. What about this number? Whatever it is a positive integer, right? Times 25 plus 1. So it's of the form a positive integer times 25 plus 1. That means when you divide this number by 25, the remainder is 1. So we have proved this. Okay. In fact, actually I think we should not have verified this also, because we can start taking 25 common out when we have n at least 2. So you need not verify this also. You can take n greater than or equal to 2. That will get the job done. Because if we don't have n greater than or equal to 2, if you have n equal to 1, then in this expansion there are only 2 terms. Remember, when n is equal to 1, the number of terms is 1 more. So these 2 terms. Among them, this 5n gets cancelled with minus 5n, so we are left with 1. Okay? So this is the thing. Let us look at some more problems like this. Some 1 or 2 problems like this. Let us first of all try to expand this. It's even a higher number, 6. So to find the coefficients, we can use the coefficients of the 5th power. If you remember, 1, 5, 10, 10, 5, 1. So the next row will be 1, 6, 15, 10 plus 10, 20, again 15, 6, 1. 6 is 0, x to the power 6 plus 61 x to the power 5 times 1 by x plus 6c 2 x to the power 4 times 1 by x square plus 6c3 x cube times 1 by x cube plus 6c4 x square times 1 by x to the power 4 plus 65 x times 1 by x to the power 5 plus 66 1 by x to the power 6. So if we simplify this, now we know the coefficients. This is 1. So this first term is x to the power 6. The second term is 6 times x to the power 4. Then the next one is 15. 15 times x to the power 4 by x square is x square. then 63 is 20. You see that here they cancel and there is no x. Plus 64 is again 15 divided by x squared, because we have higher power in the denominator. Plus 65 is 6. 6 divided by x to the power 4 plus 66 is 1. So 1 by x to the power 6. So this is the expansion. Okay, let us take this question. Prove that summation r varying from 0 to n 3 to the power r NCR is equal to 4 to the power n. This is rather easy. Four to the power n can be written as 1 plus 3 whole to the power n. And if you look carefully, the binomial expansion of this is nothing but this. You see, we are not taking I because here the index is given as r, although it does not matter, but still r is equal to 0 to n NCR 1 to the power n, but 1 will not appear. 1 to the power n minus r times 3 to the power r. So it's nothing but this. So this is the proof. Okay. Now let's look at two observations regarding this expansion of an expression that looks like this. Okay, by the way, this is called binomial theorem because there are two terms. If you have more than two terms, you will have multinomial theorem. In fact, it's there, but it's not used much. You can try to write an expansion like this, where what you do, you treat this a plus b as one number and treat this c as another one. So you write the expansion for this. Then in each term you will have powers of a plus b that have to be expanded, all of them. So it becomes unnecessarily complicated, and although this formula for binomial theorem itself is somewhat complicated, involving coefficients and whatnot, but trinomial, tetranomial, so those theorems are really they are not used in that way, because you can expand everything after all using binomial theorem itself. So we want to make two observations. Now the first observation is rather easy. Let's recall some of the expansions that we started this discussion with. A square plus 2ab plus b square a plus b whole cube is a cube plus 3a square b plus 3ab square plus b cube. Now the first observation is that the number of terms in these expansions is one more than these exponents. If the exponent is 1, there are 2 terms. The exponent is 2, there are 3 terms. When the exponent is 3, there are 4 terms. What happens in general? When we have a plus b to the power n, do we have n plus 1 terms? In fact, that is true. For that, we need to write this sum without using the summation notation. So what this sum actually is this nc0 a to the power n, you know very well, nc1 a to the power n minus 1. Let me write this as b to the power 1 instead of simply writing it as b. nc2 a to the power n minus 2 b square plus etc. plus ncn b to the power n. Now, how many terms are there? If we neglect the first term for a moment and consider the other terms, if you treat this as one term, you can see that that fact is available here as the exponent of b. This is one term, this is another term, so here we get two terms, so here you have 2. So when we reach the last term, we will have n terms, excluding the first one. So there are n terms in this sum plus one extra term, so n plus 1 terms. So this